Hello, everyone, and welcome to the second session of our fall 2025 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, this is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Tianxing and Estéban will be presenting their work. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat feature. I'd like to point out that this meeting is being recorded and will be made available shortly after. Thank you all for being here today. So now our first speaker is Tianxing Dai, who's a doctoral candidate here at Northwestern with Professor Marco Ni. Tianxing focuses on public transit, applying tools from urban planning, economics, optimization, data analytics, and machine learning to address transportation problems. Prior to joining Northwestern, Tianxing earned a bachelor's in civil engineering with a minor in urban and regional studies from UCLA. Tianxing, whenever you're ready, go ahead and share your screen and you can start your presentation.
Okay. Let me share my screen.
Are you able to?
I think so. Yes. Just making sure. Are you guys seeing the presentation? Just start
Yeah.
slideshow. Okay. Yeah. Yeah. Thanks, Pablo, for the kind introduction, and I'm happy to present my research. The title is How Our Values and Means Shape the Optimal Transit Fare Policy. So this is a joint work with my advisor, Marco. I'm happy to present here. So just since we're talking about fair policy, we should really begin with a background on how transit is financed around the world and in the US. So actually, transit is well known as a public affair, right? It's mainly operated and owned by the government or public entity. So if you look at the chart on the right, you will see that, say, around the US, in Europe, and in China, most of the public transit services are owned by the public government or a transit agency. There are also some rare cases, such as in Japan and Hong Kong, where it's privately owned and they can actually profit from it because first they set a high fare and then they also have a very high ridership. But most of the cases is publicly owned. So subsidy is definitely needed. And if you look into the US, these are the funding breakdown for many of the largest transit agencies in the US. Actually, fare only contribute to about like 40% of all the operation expenses, with the remaining come from different level of government fundings. So you see the needs of subsidy here, and then actually it is justified in for different reasons. First is you have the classical economic reason, which says subsidy is efficient in the first best way because of the mooring effect. For those of you who don't know what the mooring effect is, basically saying there's economies of scales in transit operation. With a higher demand, the optimal frequency of transit should be higher. So that justifies a policy in a more pure economic sense. And then there are also arguments that public transit is a more sustainable mode of transportation because it serves as a way to relieve congestion on the roadway, reduce emission, noise, promote safer transportation options, things like that. So it's definitely a more sustainable option for the city. So this comes more like a second best argument. And then there are also a fairness argument. So you could probably see that it's publicly owned. So there's it's definitely not market driven in a way that it will be more like policy driven. So there's where the fairness argument coming in. The idea is to promote basic accessibility for everyone in the city in terms of where they can go around and how high the fare is. So you can't really set a fare too high, so subsidy is definitely justified. And how do we actually support this operation? Where do the subsidy coming from, right? So the important question is, what are the available means? So you have the fare, which is direct user fee. And then some cities, they have the dedicated sales tax, such as in Chicago, we have the RTA 1% sales tax. tax that is dedicated to transit operation. And then in some cases where there's congestion pricing, for example, in New York City, at the beginning of this year, they started charging congestion pricing for entering Manhattan. Part of that revenue is used to fund public transit operation as well. So we call that a driver fee. So it's like a cross subsidization from driving to transit. And of course, you can have other sort of government revenue transfers, say from different loans and different funding resources available. Just some background here. And then since we know that subsidy is justified and is required, why not just go for like full subsidy, right? Full fare free transit. Just get rid of the dependence on fare totally. And this idea is actually very politically attractive around the world. People have practiced it, advocate for it, and things like that. So there are arguments for it because it reduces the boarding time and fare collection effort, which sort of align well with the efficiency argument, right? You can operate transit at a efficient way, faster speed. And then, yeah, that's just a first argument. And then it increased the transit ridership a lot, right? Because of the zero price effect. This aligns well with the sustainability argument. You can encourage mode shift dramatically from driving to transit when you reduce the fare to zero because people are more inclined, more attracted to the free goods and services, such as fare-free transit. And then finally, you had the fairness argument. Basically says it can relieve the financial burden for the disadvantaged population. They no longer have to pay anything to access the service. We see the goals of fare-free transit actually align well with how the subsidy is justified, which kind of makes sense. We have been talking about fairness quite a bit, but actually, what is fairness, right? It comes in our values and what do we believe as fair. So that's how the values could shape the optimality in the fair policy. So I would say that the mainstream or status quo is what we call utilitarianism. The idea is to maximize the total utility for all groups. In a sense, it promotes equality because if you think about it, everyone's utility counts as just counts equally in the objective function in a way. So maximize total utility is one way you can think about, is it fair because everyone counts on the same? However, this does not have any like equity implication or like preferential treatment. That is why we think there's an alternative paradigm called egalitarianism, where preferential treatment is sort of justified. I'm going to quote John Rawls in his book, Theory of Justice, where he proposed the idea of different principles. So justice is achieved by maximizing the primary good enjoyed by the least advantaged member of the society. So you can see this is totally different from utilitarianism. This is representing equity because there's preferential treatment, addresses the vertical equity issue. So this is another argument for fairness. So there's how the value coming into the play here. And then even for the fare-free transit, there are different types, right? There are different sort of policies that support fare-free transit. What we understand fare-free transit is normally the system-wide fare-free transit, or what we call full FFT or FFF. It just says you are making fare-free for everyone, and because of the benefits that I mentioned earlier, faster boarding, no fare collection efforts, and increased ridership. There are also downsides to that, right? With the increased ridership, there could be crowding issues, there could be safety concerns. And then think about who the primary beneficiary is. It's actually the frequent users, not necessarily the disadvantaged population. So I'm going to put a question mark on the equity argument. And more importantly, there's a finance issue because you are sort of foregoing all the fare revenue needed to sustain the operation of the system. Alternatively, you can have a main space partial fare free system. We call it PFF, where you only have fare free for the disadvantaged population. So this has been practiced actually worldwide, and it's actually written in some of the laws or guidances where it's made free for like elderlies or lower income population. It varies by cities and agencies, but it's being widely practiced. You can just give out like a fare card, a pass for free, and then they can use it. So it's easy to implement. A primary benefit I want to mention here is that the benefit really goes to the targeted group. And then for the other, no matter its benefits or drawbacks, there's not much significant changes. And it has minor impact on the finance side. So I've talked about different parts of the question a little bit here and there. I'm going to summarize my research question. First is how our values define the optimal fare policy. How do we define optimal depending on our values? And then how our means shape the optimal fare policy, right? Depending on how much resources available, different fare structures, things like that. And then the side question is fare-free transit, whether it's full or partial implementation, a good idea or not? To address those questions, I'm gonna use a stylized model and then use a case study based on Chicago to show my results. And this is actually just a map for the CTA transit system in Chicago. So I'm gonna talk about my model here. It's a very simple model, a stylized model. I assume that the city is a square city with a grid network, which actually resembles what Chicago is, if you just remember the picture I showed just now. And I'm gonna assume that the demand is uniformly distributed spatially. However, the travelers will have different income distribution. So they are heterogeneous in terms of their average daily expenditure, how much they spend on the goods and services every day, and follows a distribution like this. You have more poor people than rich people here. And then people are making a mode choice between bus and car, just two modes to simplify the analysis. And then we're designing a transit service in terms of headway, stop spacing, and line spacing. So these are just standard sort of design variables in transit design literature. Headway is just related to frequency. The mode choice is utility based, right? People are going to choose the one that the mode that gives them a higher utility, and then utility have different components. I'm going to simplify things and make sure it only depends on two components. The first, what we call it as accessibility, how much the transportation service provide, what's the benefit of that? It increases with the distance travel within a certain time by this mode M. And then the other is consumption of other goods and services. So after paying the fee, the user fee, and then taxes, what are the remaining expenditure you have for other, say, leisure goods and services that contribute to your utility? I'm going to talk about accessibility first. So I'm not going to go into the details of the equations I use in the model, but just a general direction of how things are related to each other. So accessibility increases with speed. Speed actually is related to congestion. It decreases with congestion level. And I'm going to capture congestion using a fundamental diagram. In this case, since it's a network, I'm going to use a macroscopic fundamental diagram that looks like this. It's basically a flow density relation. The speed is just the slope. And then the density will increase with the share of driver here. So actually you notice it's endogenous because think about it, the share of driver is an outcome of the mode choice, right? And then the mode choice depends ultimately on the share of drivers. So there's endogeneity in the model, which is what we call as congestion equilibrium. So there's need to solve like a fixed point system somehow. And then I'm going to talk about the finance side, where these are the means. Like I'm going to impose a fare structure, a two-tier fare structure where there's a discount fare R1, a full fare R2, and then a threshold. Basically, those who qualify as a discount fare should be having having a ADE, the expenditure less than the threshold. Otherwise, they have to pay the full fare. And then you have other means available like dedicated sales tax, T, or driver fee, tau, right? So this is a financial policy vector. And this defines the consumption pattern or the expenditure function. The first term is just the expenditure remaining after tax and this spending on necessity, this E naught. And then the second term is the transportation cost. It's not only mode dependent, as you see, CD and CB are different. But it also depends on the income or the expenditure, right? If you have expenditure lower than ER, then you pay R1, otherwise R2. So you see that the mode choice is ultimately determined by both accessibility that I just talked about and also the finance variables and the consumption pattern. A very simple model, just two components here. And then I'm going to show how the mode choice can be simplified with an additional assumption that extra spending power adds more utility to driving than to transit. So this gives us a benefit of having this proposition, an important result that simplifies analysis a lot. So there actually exists an indifference ADE, like E hat. So basically, whoever have ADE less than E hat will ride bus, poorer people ride bus, and rich people will drive. And because of this, you can represent the share of drivers just using this integral. And then the mode choice equilibrium condition or the fixed point system is really just this simple equation. I read it in the simple form, but if you expand out, it's a lot of arguments and terms and related through different equations. Basically, this says the utility for driving for this indifferent AD traveler is the same as his or her utility for taking the bus, right? And then I'm going to talk about the transit agency operation side. So the total budget can have different components. So if you remember the mode choice structure, you'll have the poorest section who choose transit and pay R1, the discount fare. And then R2 is the middle part who take transit and pay the full fare. And then you have the rich people who drive and pay the driver fee. And then these bounds are actually the bounds for the integral, right? This is how you aggregate the total revenue from different segments of the population. You sum them up, and then you get the total budget. And on the cost side, it's depending on the design variable, headway, and sort of spacing, which is more like network density. So it has two components. One is distance-based, which is related to fuel consumption, and then fleet-based is related to the labor, like the bus driver's wage. And then this is how you relate mode choice to budget. You have the driver fee revenue, you have the fare box revenue, you have the tax revenue and exogenous subsidy that overall just sum up to the total budget. I'm going to present the formulation here. This is a step-fair transit design problem. In the utilitarian design, right, and this is the first value that we impose. You maximize the total utility, just summing up the utility from everyone, and then subject to two constraints. One is a mode choice equilibrium constraint, and then the budget constraint. Very simple if you write it out in this way. And then alternatively, you can have the egalitarian design, which instead of max total, you max min, right? Max minimum utility, which in this case, the minimum utility is either the utility of the poorest traveler or the poorest traveler who pay the full fare. So you can prove that it's either this guy or this guy. And then we talk about fare-free transit and their benefits, right? The full fare-free implementation. There are things that set it apart from the normal sort of transit operation because it's more efficient. So we have to sort of count for it differently. So the first effect, first feature for full fare-free implementation is the zero price effect. Everyone will perceive transit more than what it truly is. So you need to scale up the utility function, and this is what we call the perceived utility. And then it has better boarding efficiency. The time for boarding will be reduced because you can use both doors to board and alight. So this basically means the average speed of bus will increase because you spend less time at each stop. And then there's also cost saving, right? Related to labor material cost. You don't have to implement the fare collection machines and things like that, which scale down the cost parameter a little bit. So this is a different problem because the constraints are slightly different. I call it the fare-free transit design problem, where the objective function are the same, but the constraint is subject to the perceived utility equalization and then also the budget constraint under the updated parameters. And you have to force the fare at zero. So there's actually a discontinuity in the model, like the two design problems are different because of the parameters. So how do we determine the ultimate fare policy? Is you first solve the SFTD, and four cases may arise. You can have a uniform fare design, you can have a partial fare free design, a full fare free design, and a standard discount fare, like the different fare policy structures. And then you solve the FFTD independently with consideration with all the features I just introduced, and then you can compare the two solutions to get the optimal policy. So now let's look at the case study and the numerical result. I'm going to calibrate this model using some characteristic of Chicago and the CTA. The utility function is a Cobb-Douglas form. Accessibility and expenditures entered into the function in this way. And then I'm going to test three hypotheticals, which relates to different financial resource availabilities. So the first case is unrestricted in both tax and driver fee. Sometimes a tax can be high, but it's actually not like realistically practical. So, but we just want to test whether under unrestricted case, what's the outcome? And we mildly restricted it by 1% tax cap and driver fee $1. And then finally, we have a severely restricted case, which is likely the status quo condition where 1% tax is allowed, but there's no driver fee revenue, no cross-subsidization. So I'm going to look at the first step fare design first. So if you just zoom into the optimal fare policy here in these two columns, you see that under no restriction, utilitarian and egalitarian design both prefer partial fare free, 0 for the lower income group, but a positive fare for the positive full fare. And then this is the utility distribution or utility profile for people of different ADE, right? You see the increases, and because of the fare, there's some gaps here and there. The poor and the rich are doing better on the utilitarian, but you notice that actually many of people actually are worse off compared to even the status quo, right? Yeah, just some takeaway from that. And then if you move on to the mild restriction case, you see that the utilitarian will prepare partial for free, but egalitarian will start to charge a little fare for the lower income groups. So as a result, the outcomes will be similar, the utility profile, except for the bottom end of the spectrum for the ADE. More travelers are actually better off compared to the previous scenario, so above the black line. And then under severe restriction, utilitarians prefer a uniform fare, egalitarian prefer a standard discount fare. You see they're all on top of each other, similar to the status quo, but there's still some differences at the lower income group. Yeah, basically it's a trade-off between this very poor people and like the second poorest, because you are charging them different fare. And then if you compare the fare-free transit design solution to the step-fare design solution, you see that in both utilitarian design and egalitarian design, full fare-free outperform the step-fare design under both model principles. You see that the difference is very small under utilitarian design. They are actually like identical. So just to keep in mind that. And then if you look at the utility profile here, you see that full fare free generally improve the utility. The solid lines are above the dashed lines, except for the poor people in the utilitarian design. So an interesting finding here. And then ultimately, I'm going to decide the optimal fare policy under different financial constraints, different means we have, right? And this is the outcome, the optimal fare policy structure regimes. So I'm going to summarize it like this. Uniform fare is only optimal when when the financial constraints are very restrictive. It has a broader region utilitarian design. And then full fare free policy is typically available when you have a high tax cap, when you're allowed to charge a high tax to fund transit. It's more nuanced for the egalitarian design because in this region, as we have shown before, this partial fare free and full fare free are actually comparable. They are very similar. The shape is weird, but they're just the outcome is actually very similar. So I'm not going to distinguish those. But for the utilitarian design, it only works when the tax is low and the driver fee is high. And interestingly, the discount fare is only egalitarian when the tax is low and it's not utilitarian anyways. So you see that actually the utilitarian is more receptive of the full fare free policy. So the counterintuitive idea here, it has a larger blue region than the egalitarian plot. Mainly because of the service efficiency, system-wide efficiency proven, right? If you think about it. And then the idea that ability to raise tax is really important compared with how you charge drivers. So just quickly summarize the takeaways. First is that to answer the first two questions, full fare free, like this policy can be both just and utility maximizing. It's optimal under both values. And then if one is allowed to freely raise tax and charge drivers when you have the means to support the operation, right? And then tax is more effective. You actually see that under modest financial constraint, it actually is more popular policy, right? More people are better off. And then finally, I'm gonna say that full fare free policy is less egalitarian than step fare or partial fare free policies, right? Because think about it, egalitarian, you need actually targeted policies like a step fare design. You have a discounted fare, or you can just make the the trend totally fare free for only the lower income group, right? So when progressives are promoting for that, they need to be careful in their arguments, right? If they promote system-wide, it's fare-free implementation, then it's really be more of a efficiency argument. Because if you want to just help the poor, then I guess giving them a pass may be a better or more direct approach. So yeah, that summarized my presentation, and then thank you so much. If you're interested, you can scan the QR code for the preprint. Thank you so much.
Thank you, Tianxing, for your presentation. And now we have a few minutes for questions from the audience. If anyone has questions, you can write them in the chat or you can just speak up.
I'll ask you a very quick question. I was
Yeah.
curious if essentially individuals, they are fully defined essentially by their income. And basically, the spirit of the question is, and I think you may have seen that presentation as well. It was given by Sergio Jara Diaz at ITEA, and he was basically capturing essentially the other characteristics, the time that it would take certain individuals to board buses. And in particular, he was thinking about essentially elderly passengers that often get discounts and so on for fare. And so he was arguing that that this has a really negative effect on the performance of the system. And so I was curious a little bit about essentially other variables being captured in your model, Tianxing. Nice work, by the way. I should have started there. An excellent presentation.
Oh, thank you. Yeah, it's an important question here because in this model, indeed, only the income is what differentiates the travelers. Just for the pure sake of analytic tractability and also for the solution methods, because this is a modeling approach. Of course, I get that like other variables, other social demographic characteristics will be important. You can have multiple dimensions to characterize a traveler. And then you can have different policies for them as well, like elderlies, whether you can have an dimension just age, and then you can have different policies based on their age as well, like maybe fare free policy for them, and then maybe you can combine the criteria. There's all possible extensions for this model, and I think it's capable of doing that. Although I think to pursue that direction, more econometric kind of analysis will be making more sense because as you said, like you can have different components within the trip. Like when they board the vehicle, the time taken will be different, and then you can have all kinds of things that are summarizing the model. And then somewhere you can like make a larger choice. You can have when you have all those complexity in the model, then I guess you have to define the utility function more carefully, and then the choice as well. So yeah, a very practical and thoughtful comment.
We have time for another question. Go ahead, Jürgen.
Maybe I have also a quick question. Thanks for this great presentation. I have two questions, actually. The first one is, how do you validate your model? And the second one would be, what is the next step in your research journey? So what do you want to do with this now?
Mm-hmm. It's how do I validate this model? I would say it's a little bit hard to validate at this stage because it's very theoretical. It doesn't capture like the common features in social demographic variables. I guess the key is to review sort of economic insight, like what do we get out of this model? Right, just review the direction, not really exactly the numbers or the optimal designs. Because I'm just saying here that it will be good to know that to review that full fare free policies have this efficiency improvement, but it's not like well targeted if you want to pursue certain policy goals. So just to raise some sort of like caution here when people actually advocate for it, it's not necessarily like a perfect thing, right? It has the financial constraints, it has all kinds of the details. So I would say just revealing the direction here, the intuition here is more important than to validate it. And then the second question regarding the future direction, right? First, on this end, the fair policy, one direction is like what Pablo recommended, just to include more variables and how you define the travelers. Another direction will be to consider more realistic structure and policies, especially under the current context where the transit agencies are slowly recovering from the COVID-19 pandemic. The ridership is still not there. What is the underlying mechanism behind this low ridership, and how does the transit agencies react to that? Is fare-free transit good under that context, where they already receive less revenue anyways? And then how about just foregoing that, right? Is this still applicable under that context? And how do we have a better sort of financial mechanism to support sustainable transit operation? Just basically capturing what is different sort of as we move into the future. So yeah, hope that answers the question.
Thank you, Tianxing, once again for your answers and for your presentation. And now we're ready to move on to the next speaker of our session today. Our next speaker is Estéban Nocet-Binois, who's a PhD student at Princeton in the Complex Infrastructure Systems Group, working with Dr. Jürgen Hackel. Esteban's research focuses on developing tools for analyzing infrastructure systems, drawing from differential geometry, statistical mechanics, and information theory. Esteban, when you're ready, you can share your screen, begin your presentation.
All right, so we can start. So today I will introduce kind of the work I'm doing here in Princeton. So we are working on infrastructure systems from sort of the complex systems approach. And I will explain a little bit what it means, at least in my case. And the goal today, and the goal today will be to cover first some element of, I guess, context about graph data, what I mean by this, and what I study about it, what I want also to pursue in terms of research. Then I will kind of introduce the topic from transport phenomena in physics and how they translate over networks. Then I will introduce what we mean by graph Laplacian, which will be an important element of this. How it also plays a role in applying sort of Fourier analysis on graphs. And then some element, in this part, I will also present some results of the project I've been doing over this year. And then I will conclude with some future research that I'm looking at. So for some context, I am broadly working on graph data. And what I mean by graph data is having a graph, having data on a graph. So far, it's mostly having specific concentrations or quantities that I'm looking at every node. That could be angles or I don't know, concentrations of subchemicals at every node. And then I just want to study structure and especially how things diffuse on that network, given that we can look at those trajectories over time at every node. So you might have a snapshot of your graph at every point where you would know a specific quantity at every node. And from this, the objective is to learn structure and infer some properties, I would say. And some key research axes that are on this subject are all elements of harmonic analysis and Fourier analysis, but also being able to learn the underlying manifold. And I will explain a bit later what I mean by this, and also in general, being able to retrieve the sort of diffusion geometry that you would suppose is generating your data. Some research gaps. I guess the general approach that I'm trying to take is more of an inverse problem. So you look at your data and you want from this to infer from network structure, your network structure, which I find to be a good way to bring also some of the network science to the engineering field. And on the more theoretical side, there's a whole bunch of problems that are needed to be addressed because in itself applying most of this Fourier analysis to networks is already an important task on its own. And I can also, I guess, point to some problems already that would be interesting. For example, taking into account tensor geometries at every node. So far, I'm mostly speaking about scalar concentrations or scalar quantities at every node. But of course, it would be interesting to take into account that at every node, you might have several components. And those several components might be, it might be interesting to look at them as tensors or as something else than just something that you could divide for every component. So that's one element, but there are other elements that I might come back to later, more as a conclusive thoughts. So now to start thinking about this approach, we can, I guess, see also what are some elements in common with other elements in physics and what would be new with our setting. So, studying transport phenomena in physics is a pretty common thing. I took like 3 different examples here. For example, if you have particles flowing or being transported on a confined area where now you have 2 planes on either side, which come with some perturbations at each side of this space. You take on the middle one, for example, particles flowing through porous media. And on the last one, it's already a little bit different because now you have a Brownian motion over a spherical space. But what I'm trying to do with this is to also show some similarities. For example, the fact that in those elements of physics, what you would often do is to look at sort of Brownian motions or particles that would be represented as stochastic processes. And then you would try to find from those microscopic stochastic processes, you would try to sort of average those past trajectories and find from it some macroscopic behavior. So for example, if you're looking at those particles in a confined area, you might want to look at the conductivity, which is a macroscopic property from some of the some assumptions on the stochastic processes behind it. So that's one similarity that I would say is also something that you find on network science. Another one that I will also point to is that looking at diffusion is at least fairly easy, as in you can look at a Markov matrix, for example, which gives you some transition rates, and it's more of a local node-to-node jump that you're trying to explain. But as soon as you want something more complicated, for example, if you have reactive terms, then now you need to know joint distributions. So for example, you want to be able to describe one occurrence of your states across all of your nodes if you're looking at a network. And those kind of things have huge combinatorial limitations. Usually in physics, what they would do to cope with this is using some approximations. But a lot of those approximations are usually using the fact that we only look at local geometric features. And something that I want to introduce now is the fact that and when we're looking at the networks that we are looking at, those local features are actually not the most important. Unlike this case, we have pores, or where we have just the like surface energies or these kind of things. In the networks that we're looking at, actually global properties and global topological features are actually almost more important, or at least you cannot just average them out as easily. And that's also one major limitation, and that's also where network science becomes different, I guess. So for example, in this example, we have a river network, which already starts to be looking more like something that we are looking at. And something that was found in this paper, for example, is just that you have this spectral gap when you look at the cumulative distribution function. You have all of a sudden this spectral gap, which kind of shows is linked to this branching pattern in your network. And it goes to show that you have now macroscopic behaviors that are actually disruptive, and that needs to be accounted when we want to develop new techniques, basically. And in general, like this case here is the water distribution system in New Jersey. Is it zooming out? No. How can I? Oh. Okay, it's a little bit zooming out. Anyway, zooming in, I mean. So typically in those very complex networks like this water distribution, now you have actually patterns, and those patterns will actually define your distribution, your diffusion much more than some easily averaging stochastic properties. And so that's something I wanted to introduce here, that the topology is something that we want to take into account. And I guess from there on, we can introduce some one important operator on graph, which is the graph Laplacian. And it's directly, and we will actually develop this link between the two, but it's directly sort of discretization of the Laplace operator that you might know on the Euclidean space. So just like in Euclidean space, you will also first your Laplace operator is supposed it's giving you the divergence in gradient, so it's telling you how different the gradient is at a specific point with respect to the infinitesimally small neighborhood, and you can describe this literally as the diffusion in both x and y direction. So you might describe it as on the x-axis how it diffuses east and then north, and pretty much the same way actually we can look at for the discretized version, but now you don't have just an x and y direction or east and north. Now all of your directions are given by your adjacent neighbors, and so theoretically you can have much more orientations than just east and north, and that's also where more complex things are coming in. And now I will also hint towards another element, which is also that we're actually looking now at graphs not being just discretization of a flat space like the Euclidean space. We are looking at graphs as a discretization of a manifold, of a curved manifold. That's actually where those global topological features happen. And that is actually a much more accurate way of thinking about the graph, because I mean just variations about the in and out degrees across your whole network already give very different curvature properties that makes it much more meaningful to think in terms of curved manifold. And in fact, you have already it was the Riemannian hypothesis that under some uniformity in sampling and some rates of sampling, that you would converge the Laplacian operator on your graph towards the Laplace Beltrami, which is the generalization of the Laplace on a manifold. And this is a way of thinking about your Laplace operator as discretization of the Laplace Beltrami on the manifold. And in particular, it also applies for the Fourier transform. So you also define the Fourier transform on manifolds using the Laplace Beltrami. And quite the same way, you can apply it by looking at the eigendecomposition of a Laplacian matrix. And that's something that we are using here. And that's what makes also the Laplacian matrix interesting when we look at graphs. Although, as I said before, it is still only your diffusion part. So it's not telling you anything about reaction processes, but at least you have something that you can look at and use to decompose your signals into global modes of variations with different energy related to all of those modes. And especially this matrix allows you to apply the frequency analysis on graphs, which is something we are interested in. So now the project that I will present is a first one where I tried to sort of apply those elements of Fourier analysis to graphs. And I first step towards this was to first try to learn a correct Fourier basis from data, coming back to this inverse problem approach, because the issue is that we often look at infrastructure systems with streams of data at every node, and you might assume that they are stemming from a matrix with known weights and use those weights to derive the Laplacian. But one issue is that you can only do so if you assume that your graph data is actually generated by this matrix. But it could be interesting to go the other way around and take your data and try to find the best basis that would explain the most efficiently possible in the most efficient way those signals. And by expressing them efficiently, I mean that you could theoretically take the k largest modes of your eigenbasis and use them to reconstruct your signals back, and then look at how well you reconstructed your signals. So that's going to be the way of evaluating the performance, basically, is to look at how well you can reconstruct your signal with how few modes, basically. Because if you had a purely random matrix, then you would not capture specific tendencies in your data. And then if you take a random node, any signal, basically, the probability that you would be able to express it in only a few of those modes would be very, very low. And some element that I will also address in this talk is some elements about the rank efficiency of your covariance, which is linked to the sample complexity. So how much signals do you need to learn your Fourier basis, which is very important, especially with respect to the size of your graph. And I will come to this. And then some of the elements, but the most important is what are the model assumptions with the following framework that I will give you. So yeah, as a first step, maybe let's just explain what I'm using. So X here will be denoted as your signal matrix. So you just are stacking all of your signals. So those signals are just a collection of all of your scalar values at every node. And now you're looking at a stack of those. And the sample covariance is this one here that we will be using actually to learn the Laplacian. The Laplacian is denoted like this. And we will, okay, so it's not, the lambda is not appearing here, but you have your lambda in between, and this is your eigendecomposition of your Laplacian matrix. So U are for your eigenvectors, and your lambda is your diagonal matrix with all of your eigenvalues. And so now the first element will be that one way, maybe the most intuitive way that you would want to learn your Laplacian given data is by looking at your covariance. Because so the Laplacian matrix, you can think of it as like some average commute time between two nodes. And so the more correlated they are, so the more they evolve together, the shortest you would assume to be that commute time between two nodes. Because you would assume that very quickly, if you have a specific quantity at node I, it would transmit to node J very quickly. And then you would explain like this sort of reciprocal relationship between the covariance and the Laplacian. And this you can express it as considering your Laplacian metric as the precision matrix of a multivariate Gaussian density. And this is, of course, a fairly convenient framework because now you can express your maximum likelihood objective such that you want to find the best precision matrix that explains the data that you have. And do I write it? Okay, so the maximum likelihood objective is here. And that's basically the objective that you're trying to find the best Laplacian matrix here that maximizes this term here. And we can note already that we have two important terms, the minus trace of L sigma. So I think I changed something on my latex so that it doesn't appear anymore. But I have also a sigma here. So L sigma, taking the trace of L sigma is basically aggregating your total variation. And now you are just trying to minimize this. So you're trying to find the smoothest explanation of your data. And by smooth, I mean, which I wrote here. No, I think I wrote it before then. Oh yeah, a signal is smooth if the value do not change drastically along strongly connected node. So that means that exactly this, if you have a large connection between nodes, then you don't expect them to covary very little. So you expect them to covary a lot actually. And that's what we call a smooth signal. So for example, if you had two strongly connected nodes according to your Laplacian, and your data would go completely not alongside one another, then it would be a very non-smooth graph. So of course, you want to first find a Laplacian that would actually explain your data, and then being able to capture from new data whether you do lose some of this smoothness, which would be indicating, for example, that maybe at a specific node, now all of a sudden something happened, maybe a leakage or something that explains this non-smooth result. But you can only use those if you have a matrix that actually do capture those dependencies. So yeah, so this minus trace of L sigma is the smoothness that you're trying to minimize. And the first term here, the log determinant is here to give you some better spectral properties because it's basically giving you the product of your eigenvectors. And now it's trying to maximize those given that it's trying to minimize the smoothness. So it's trying to find the better fit to your covariance while having a spectral profile that is as high as possible. And in particular, taking the products so that you don't want to have already in your spectral in your spectrum, you don't already want some discrete result where you might have very like only a discrete set of eigenvectors, basically. So you want to make sure that the product of all of them is just as high as you can. So that's how you would interpret this, and that's basically the direct derivation of your maximum likelihood for multivariate matrix. Some elements that are problematic here, however, is that if you enforce Laplacian constraints, the Laplacian is actually singular, which means that you would have a determinant of 0, and the log of 0 is not defined. So that means we already have an issue here. One way that we could cope with this is by learning a shifted Laplacian. So now you just shift your Laplacian by loading your variables. So now you're learning a sort of biased Laplacian. Another way is also to just not enforce this, in which case you are just learning basically a covariance structure, as in it should be positive semi-definite, but strictly positive semi-definite. So you don't want to learn something that might become singular, for example. But something else that can happen actually is that since we are minimizing the smoothness with respect to a covariance matrix, if that covariance matrix is already rank deficient, then you will converge to something that is rank deficient. And then even if you don't enforce your Laplacian constraint of singularity, especially, then you will also learn. You will also have instability by having your matrix going towards a rank deficient solution, and then again, the log would be not defined. So one first approach is to not take Laplacian constraint leading to singularity and learning a shifted Laplacian. But then also, one way to do is if you still want to make sure that you don't converge toward a rank deficient solution, is also to add this sparsity constraint, which has two benefits. First, that you are learning a sparse matrix, which makes sense because we know that the result should be sparse. So adding this sort of constraint, which add weights to something that you're trying to minimize for every number of edges that you add. And basically the goal is to avoid having something where if you have highly non-covariant results for a specific node, it will more and more converge towards 0, but it would just shrink towards 0. Something you want to do is to have some form of, soft switch, such that at some point it will just, for the purpose of minimizing this objective, it will just put it to 0. And the advantage with this is that you also putting something to 0, you will also load other values, which will also help with the stability. And then another one is to actually decompose your log determinant term into one part that is taking the squared Frobenius norm of your off-diagonal elements, and then you treat each of your diagonal elements separately. And this basically gets rid of your log term, which is a convenient way. And there's been, I think, some papers proving that they do provide the same solution, basically. So this is just to show you what I meant by the issue with the rank deficiency of the sample covariance. The issue that with this, basically you need to have at least as much signals as nodes to have a rank full covariance matrix. So that theoretically you would need to wait to be after this threshold. So in this case, this is actually where you get as many signals sampled as nodes. But of course, that's an issue. And even thereafter, it's a log scale. So it's actually very slowly converging. So the best thing that you would want to have is something that learns before and something that doesn't take like such an important scale to improve. So that's the first element. And of course, that's especially important for us when we look at infrastructure systems, because if we have very large systems like a water distribution systems or power grid, you don't want to have to wait to have more signals than nodes, because that would be just a crazy amount of signals. That's the first result on I'm looking now at how the bases that are defined by those matrices that you are learning, how they are converging. And I'm doing this here, it's just on synthetic data. So I'm literally creating signals from a multivariate density. And I'm looking at how those algorithms perform. But something a bit more interesting is now we are actually applying it to some signals that we generated using EPANET. So now we just simulated the nodal pressure, so the pressure at every node. We simulated them using the EPANET software. And now we tried to see how well we would be able to perform with our two algorithms in reconstructing the signal. So that's what I said before. Now we want to take only the most significant coefficients alpha, which is this term here, and we want to use those one to project and decompose your signals into each of those eigenmodes. And now only using k modes. So you start with only one mode, and then you go to full, like all of your modes basically. And you want to see how fast you are able to recover all of them. This is the reconstruction error. So the smallest reconstruction error, the better. And this is the cumulative energy. So now kind of looking at how much energy you gain by adding each node every time. And so the sharper the increase, the better. And something that we see is that we are consistently able to outperform the result that we get by just looking at the constructed Laplacian. So a constructed Laplacian would be just looking in your weights and deriving like some weights that you could look at for the water distribution would be, for example, the pipe length. Or you could introduce like some differential in altitude or something like this, but just physical parameters that you know about your network. And from those weights, you can already derive a Laplacian. But something that we see that we are able to outperform it. But some elements of limitation that I want to introduce here is that those things are highly relying on having a good covariance structure, or at least a covariance structure that is preserved and that you can rely on to basically fit a well spectrally behaving precision matrix. That's more or less what we've been doing. But then it means that you need to make sure that one, your covariance structure does reflect your Laplacian, and especially, I mean, in general, your diffusion processes. And also you need to have something that's a covariance structure that would be preserved. I mean, it could also happen that you are losing those properties just from some data paths. So for example, if it just so happened that you have some shift in the way you sample your data at every node, and one was just sampled a little bit before, so you would have the same pattern, but just shifted in time because they weren't exactly sampled at the right time, then you would get this sort of difference, which would increase the Euclidean distance, and it would decrease the covariance between those two nodes. So just those elements. So for example, if you do not sample them at the exact same rate, one would be sampled closer together, then it would also increase its self, how do you say, like time autocorrelation, whereas the other one not. So all of those elements would also easily disrupt this framework. So that's why I'm just introducing quickly some lines of research that I'm interested in. So first, it would be to explore further about those, how to extend elements of analysis that we're using either in statistical mechanics that I was speaking about, like using reactive terms, for example, but also elements extending Fourier analysis on less and less well-behaving graphs. So for example, if we have non-Hermitian graphs, non-Hermitian matrices, so if you have a directed graph, for example, where you have important flow imbalance, so going one way is actually, you have much more flow going one way than the other. This is already disrupting the orthonormality of your basis. But then also exploring question of higher order networks, and those elements are also open questions. A second element that I might introduce quickly is also, I was speaking about this issue with taking something that relies on the covariance structure, but one element is that it's also the Euclideanness of it that's an issue, because it will be very sensitive to what I was saying with just shift in time, and now all of a sudden the Euclidean distance is increased. So something I was thinking about, and also the issue that we are not taking into account that much, actually, the distributional behavior of your time sampled at every nodes. We are not actually using how they behave over time. So that's why I would find it interesting to incorporate this distributionality in our framework. So something I'm looking at right now is sort of shifting our way of thinking about diffusion from the more classical way of thinking about this, which is minimizing the Dirichlet energy of your, I don't know, temperature, for example. So if you look at this classical example of a Heaviside function of your temperature, then over time, when you diffuse it, you start by having this smoothing, and then it finds equilibrium. But another way of thinking about this is to think in terms of probability mass. And we want to look at in a Wasserstein space, so the space that has the Wasserstein distance. So now we're looking at distance of distances. And so you want to look at how points distort themselves through space, for example. And that's something I'm trying to think about by finding a way of, if we're looking at every node individually and looking at their distribution over time, then from it we could define, how do you say, a probability measure, for example. Or you could do it between path trajectories if you wanted to compare them, or between entire networks. And now thinking of diffusion as how this whole mass, this distribution, is shaped over time. Another element is direct moving to a spinorial approach, but maybe I don't know how much time, so maybe we can just conclude by saying that so the goal with this talk was to introduce some elements of Fourier analysis, some elements of I guess being able to learn structure from your data. And by structure, I mean learning global modes of variation, and how it's interesting to see that with the networks that we're working on, we have those global features that we want to take into account. And thank you very much for your listening. I'm happy to answer questions.
Thank you, Esteban. And we're out of time, but if anyone has any questions right now, if you want to ask Esteban.
So thank you for the talk, Esteban. I mean, in a way, it's exciting to see that a lot of these rigorous forms of analysis are entering in terms of the analysis of transportation and infrastructure networks. I think that normally when you would see these things, say in the analysis of resilience, you would see very simple graph characteristics, let's say, for example, connectivity or basically minimum cuts, things of that sort. And so I think it is exciting to see these things. I think that, I think that you might be only starting your PhD, but I am curious if you could tell us a little bit of some applications that you had in mind that might make some of these tools and the application of these tools a little more tangible.
Yeah, so I guess, I mean, supposing that you have a good basis, a good Fourier basis, then now you're able to decompose all of your nodes, and you also have a proper definition of smoothness, actually, and that's the important point. So now you can just detect something that would get against that smoothness. So you could detect leaks, you could detect faults, but also you could detect, because you are literally describing your diffusion of your network. So you could also be able to reconstruct if you see a specific contaminant of a water distribution, for example, with specific densities at different paths, then you might be also able to retrace the diffusion, see maybe where it was coming from, where it will go, how it will spread also. And with even more complex networks, of course, they would not meet the assumptions of smoothness and locality that we have right now. But if we're able to define also similar techniques on power grids, then we might be able to understand how a specific disequilibrium somewhere spread across your power grids, which we know is a very complex thing. It's hard to detect and see why something that happens here and propagates over there and leads to blackout much further away potentially. So those kind of things are kind of what I have in mind with those approaches.
If anyone else wants to ask any last questions? If not, thank you both, Esteban and Tianxing, for two great presentations, and thank you everyone for being here today and for listening and asking questions. And I hope I'll see you all in November for the third session of the fall edition of VISIM.
Thank you, everyone.
Thank you.
Thank you.
Thank you.
Thanks, Pablo.
Thanks.
See ya.
Thank you, guys. Bye-bye.